We did it. So, yes, before I started, thanks to the meetup and being accommodating, came down with the Rona last month and everything's good, but now I'm ready to talk about embedded programming, specifically through the lens of synthesizers. A little bit about me. I am Jack Campbell. I work at a company called Universal Audio in Boulder.
Are you hiring?
Not right now. Yeah, we go through experts and such, but mostly the stuff that I do there is not embedded stuff. I work on like things for Mac and Windows, recording studio type of things. But I did get introduced to embedded through this job when we had to port that audio software to things like guitar pedals or whatnot. And I learned it's really fun, and I learned that there's not a lot of resources that are kind of geared towards software engineers. There's a lot of like stuff for double E's who want to learn coding, and a lot of stuff for people who are just like starting from scratch and they want to learn like Python with their Raspberry Pi sort of thing, which is all great. But I kind of wanted to go over a little bit more, not professional context, so kind of a hobbyist sort of level, but if you're familiar with coding, how do you get into this new, strange new world of embedded software development? So first I'll go over kind of how what we're talking about fits into the whole landscape of things, and then we'll get into a synthesizer kind of as an excuse to talk about concepts and the guts of this thing. It'll give us an excuse to talk about things like MIDI and UART and dealing with bringing in UART and generating audio data out, and then dealing with digital audio through the amplification stage, so it comes out with the speakers. And then we'll just kind of go through where you can go from there if you wanted to continue generating stuff. So if you're already familiar with embedded development, I don't know if I'll have a lot to offer, but because I'm still a beginner myself, but you know, it might be fun to listen to see. So specifically, I want to throw around terms like these, Ego, DNA, stuff that you might not come across if you mostly do native software development in particular, and just have an excuse to make your Google searches from here a little bit more approachable. We'll be looking at a digital synthesizer that uses a consumer dev platform known as the Electrosmith Daisy, specifically the Daisy C. I've got one here, I've got the circuit kind of built up. This is just this little tiny guy, and there's not a lot of stuff kind of around it. Yeah. So I'll just be breadboarding today. You can take it further to solder things together, but I did a lot of different configurations of the audio I/Os, so it was easier to just plug and play that way. And actually, that brings us to where analog electronics fits into all this, because the digital electronics are all sitting on the Daisy, the microcontroller itself, but then there's all this analog stuff around here, and I would say that stuff is not required for this talk. I won't necessarily be delving too much into it, but there's this book that I read periodically. I've read it twice now. It's really fun. It's called Make Electronics. It's set up as a series of labs and kind of teaches you the basics of electricity, current, and Ohm's law, and voltage dividers and stuff, how to wire stuff together like this. It also teaches you how to set up your lab, how to go on to Mauser DigiKey and order the right stuff, which is not self-explanatory, things like soldering and whatnot. And then also, beyond that, the digital portion, Sparkfun has a lot of good write-ups. They're local rather than I watch.
Are you allowed to visit them yet?
I'm not sure. Not last I checked. I hope that comes back again soon, because I've never toured them, but
they had the garbage sale or whatever it was last week, and it was like $30 shipping to my house, and I'm like, I'm just not going to do that.
Yeah. Yes. yeah, so kind of want to get to the point, where you can look at a schematic like this, see the various components here, capacitors, resistors. So I know how to wire that up on a breadboard or solder it together in a project package. That's the breadboard example there. That's a headphone amplifier that we'll talk about towards the end and more. So that's kind of as far as I can go with analog stuff for now. Back on the software side, I'm going to focus on bare metal programming specifically, which I think it's a little contentious what bare metal necessarily means, but in this context, I'm going to be talking about code that you can follow the call stack down and see memory mapped registers actually being written to and read from. There's not an OS sitting in between all of your interactions. On the other end of the spectrum, you'll hear about embedded Linux a lot, which is a really cool way to develop too. But if you're just starting out with embedded programming, and especially if you haven't learned Linux yet, there's just so much to learn right away. You have to either roll your own Linux or use a build system like Build Group or Yocto and package your application with it, deploy it to a board, and on top of that, know all the bare metal stuff as well. So it's not a horrible place to start, but there's just a lot more to do and fussing around. And then I won't talk about these too much, but in your Googling you may find RTOS-based programming, which is basically you're still talking to registers a lot of the time, but you have schedulers, real-time guarantees, and then FPGA programming I released it out, but it's kind of an old can of beans where you're not actually writing program for a CPU, you're configuring logic gates or ATL, target definition language. So all that's to say, we'll talk about the first one on the slide for the rest of the time. And the synthesizer itself, this is the big version of it, down to scale. It's an embedded sound. It's similar if you've heard of Arduino or TC or recently-ish, the Raspberry Pi Pico came out. It's not similar necessarily to a regular Raspberry Pi, which you may have heard of, which would be running embedded Linux, probably. It's a bare metal platform. The thing that sets it apart from the others is that it has the audio hardware right on there. That's an 8 amp audio codec. You'll notice the text is blurred out because the factory burned down, and they're working on resupplies.
What's the song? Sorry.
Oh, a system-wide module.
System-wide module. Okay.
So, you don't necessarily, there's a lot of weird terminology between sound system module or SoC ending system on here. I think when you get like a pre-delivered thing like a Daisy or Arduino, you don't really have to worry about that. But if you're designing your own development kit, then you need to start worrying about what vendors are going to give you. And it's also got maybe more RAM port than you expect. That helps with audio data, which tends to be pretty large. So if you have a delay effect and you need to store a lot of audio in memory, it's got that on board. And then it's a microcontroller here, or MCU is STM32H7 family. If you are new to embedded stuff, when I see this for the first while, I just kind of glaze over and I don't really care about the part, but actually it's really important to know the microcontroller you're working with because the reference manual will save your sanity the minute anything doesn't go as you expect. And so this microcontroller has an ARM Cortex F7 CPU, and then just all the little guys around here, the pins, are using these I/O peripherals to talk to the outside world, sending audio data. They're connected to the memory here. And then the software part of the Daisy, because they also have software that they offer. They have their own little hardware library that sits on top of the stuff from MIT that vendors the microcontroller. There's a lot of audio specific stuff dealing with MIDI and audio. It's great. your synthesizer sound, whatever. And then the DSP library is pretty fun. It's actually a standalone C++ DSP library. It doesn't have to run Daisy. I used it in audio plugins on Mac. It's just a really small, self-contained modules that a lot of them sound really good for an open source library. But we'll be focusing on the guts of the libdaisy today because that's kind of the level that allows us to talk about things like GPIOs and whatnot. So this slide, I kind of wanted to show some bare metal code, how it might look different from code we might be used to, so that the code that you would write, or the user code, application code, might look something like this. You got an audio callback going in. Using libdaisy, they kind of have this little daisy seed object here that you interact with, and then one layer down is the libdaisy part where it still kind of looks like regular C++ that we're used to, but it starts to start kind of a hardware specific type of operation here with the DMA, and then you get one layer down, and you can write applications using this hardware abstraction layer or HAL. It's just pain and certainly C. But it starts to look kind of like this, a little bit more beloved or whatever. And this is the part, kind of the reason I have this slide, that is different from native programming a lot. This is where you actually have a memory map register to the SAI, which is a serial audio interface. You're writing to control register 1, you're writing this enablement here. And that's actually what makes it bare metal, is interacting with a physical device directly in your code. Perfect. Burners to the rescue. So this is the synthesizer flow diagram. The rest of the talk is going to be going kind of through these little blocks and just how the data flows through the device and comes out as audio. So you got this musical data coming in here, MIDI, musical instrument digital interface, okay? That comes into Daisy, and then we interpret that music data as things like pressing a note, pressing a C at a certain velocity, they call it. They put that all in their data packet, and that goes into the synthesizer. And then a program will parse that data out, and then the digital audio comes out as analog. This is what the synthesizer looks like from that flow diagram. Again, the flow of it kind of starts up with that black connector over there, and that goes through into the Daisy, through that teal wire, is where the MIDI is going in. And then audio is coming out at, there's two tabs, a left and a right channel, and then these red wires are going at a certain line level out, so you can plug this into like guitar pedal or anything that accepts a line level out, or the same connections into the Daisy are coming out on these two yellow wires that are going into headphone amplifiers. So this can be plugged into big old headphones or a powered speaker and grind it so you guys can hear it. So starting with the MIDI, the connector that we're using here is sort of a classic. It's from the 80s. It's still on many devices. It's called a 5-pin MIDI DIN. I think actually, I've seen these on old computers too, but I don't know sort of chords and stuff. But you got a synthesizer here, the microcord, which is the only thing writing on this that puts out the MIDI DIN. And then you got putting the breadboard here. So this has a MIDI output circuit that needs to be MIDI compliant, and then we need to create a circuit here to be MIDI input compliant. And what it means to be MIDI input compliant is kind of interesting. The digital data is coming into this IC here, integrated circuit, which you'll see these a lot. There's like little bugs. They're little plastic chips with a circuit inside of them, and they've got inputs and outputs as little metal connectors on the side. This particular one is known as an opto isolator. Is the 6N138. And the reason this whole circuit exists is we don't want to actually connect a microcord or whatever electrical device we have to our daisy. Because they, like we definitely have different power supplies and ground references, so if you just make a direct electrical connection between that, you'll end up with a ground loop, and so you'll be playing audio back and you'll just have this hum the whole time. So we need to get that digital data from point A to point B without plugging it in directly. And we can take advantage of the semantics of digital data. We're used to digital data being ones and zeros that are kind of abstract that we're just dealing with. But in a circuit, digital data is a square wave essentially. Like it's just a 0 and 1, that sort of thing. Where 0 volts is a logical 0 and 3.3 or sometimes 5 or other values is a 1. And this opto-isolator allows us to take that current and flash an LED here. That's what this symbol is, the triangle with arrows, light emitting diode. So just a little light that flashes. So 0, light off is a 0, and on is 1. And then there's a photosensitive element next to it that converts light into electrical current. And so you've basically broken the connection, but you've preserved the data itself. And then on this RX or receive, you get the digital data out without the electrical connection. And it's all MIDI spec compliant. So that's what MIDI is in digital data in the physical world. But from here, I want to talk about what MIDI is semantic, because it's one small piece of a very important concept in embedded system program serial communication protocols. If you think of an embedded system as a bunch of isolated peripherals that all need to interact with one another, they've got their 1 or 2 jobs or whatever, and they need to send data to other parts of the circuit. They do that through square waves or digital signals, and they don't have any intrinsic meaning. They're just a digital current, digital signal. And so there are protocols that either side implements, they know the form of the data that they're going to receive, they know which square wave is going to be actual integers that you want to parse in your program, which are going to be clock line or some other synchronization data. All of these have different semantics. The first one that I dealt with in a class was a temperature sensor, and I think that's, if you're looking for little projects to try, it was a really good introduction to writing a driver for this sort of thing. This is the I2C protocol. This is what the temperature would be coming in. There'd be a temperature sensor on this side, 2 wires coming out of it, and then a microcontroller on the other side that is receiving 2 wires, and each side has an I2C interface, sending the temperature data on the serial data A, it's the data line, in the clock. And so this is one integer that says 20 degrees Celsius or something, and then this clock line here is the receiving end, how long each of these bits is, because this could be a 0, and then another 0, and then a 1, and then another 1. But without this clock line, you wouldn't know if that was 1 long 0 or 2 zeros in succession. So the receiving end can use that clock line to coordinate the various bits in a particular byte. The synchronization for communication protocol that we want to talk about in another context is UART. You'll also see USART in some of the following slides. For our purpose, it's essentially equivalent. It's unlike I2C, a single wire, and we don't need that clock line. It's telling us how long each bit is because both sides agree on, in order to work, they must agree on the baud rate or the bits per second, how fast they're sending the data. You'll often see UART used early on in a project for sending ASCII characters. And if you set the wrong baud rate, then you've got your terminal connected reading the UART signal from your board, trying to, read whatever your printf or outputting. And you'll get garbage if you have the wrong baud rate. And that's a very common thing when you're setting that up. It kind of looks like this. It's really agnostic to the actual data being sent. There's just a start bit that says I'm sending a packet, and then a stop bit, and then stuff in between. Like I said, that could be an ASCII character in between, or MIDI packet, which is just a packet of data that gets sent very slowly, relatively to what is possible these days. It can send at 31,250 bits per second, because this spec is from the 80s. The packets themselves, they can be things like node on, node off, kind of more application specific things like I'm switching a preset or I want a trombone sound or whatever. They try to get general MIDI going so that you can tell any particular device that I want you to play a trombone, and I don't know how many things actually implement that, but there is actually a really good write-up on the smartphone site that goes over the whole history and the data format itself. So we're receiving that over 5-pin MIDI DIN, but you can actually, a lot of times you'll see MIDI USB controllers. That's what people have on laptops or whatever. And more specialized devices will use things like Bluetooth or TRS cable, which is looks like a headphone cable. So that's kind of the deep dive on MIDI. But from there, we need to get that data that we have on this teal wire into the DAISY. And that's where we talk about drivers and pins. So this is a diagram you'll see, or a type of diagram you'll see a lot. It's known as a pin out, and all of these little metal connectors on the edges of this are called pins. There are also pins all along the microcontroller itself, and there's little connections to those pins. And each pin has one or more peripherals that it can connect to. And so we need to find out which UART RX receive pin. By the way, TX is transmit, RX is receive. We could use any of these. There's UARTs here, and you can connect to UART3, UART4. It turns out we don't need to make the decision because libDAISY has it hard coded to these pins. But if you wanted to edit libDAISY, you could set it to any of these. But a question arises: how do we, in this diagram, how do we say, there's only one connector here? If you wanted to go to the UART, how would we say we don't want to send S/C data, we want to send UART data? That decision is a configuration made in the code by the user, and it's called multiplexing. And those pins with the multiple purposes that have multiple things they can do, they're called GPIOs, general purpose input-output pins. They exist so that the DAISY doesn't have to be twice as big if you want to fit it in a really small device. That is important. So we multiplex the pin to do the one thing we want, and we can't do the other thing with that pin, so we couldn't use I2C4 on that particular pin if we wanted to enter MIDI. And then we use libDAISY to set the mode, essentially. By the way, sometimes this is multiplexing is called muxing, shorthand. So getting into some of the specifics about DAISY, the library that you could use to multiplex the pins is all vendored by ST in their hardware abstraction library, or TAL. libDAISY handles that for us, so it'll set the baud rate to the MIDI rate. It'll choose the pins for us, which peripheral we're going to be talking to, and then it handles the drive aspect as well. So we need to, once we configure the pin to be able to receive MIDI data, we need a way to get it to our program. Just to show some code, this is, I think, old. I think they've cleaned this up a little bit, but it's pretty clear, or it makes it a little bit clearer, or in context anyway, how the daisy looks. I'm having a bot right down here doing some other setup, but I bring up this slide because these pins here, UPIO port V, that's what it is, UPIO V, pin 7 and 6 is not the 14 and 15 that we were talking about earlier. So where did I come up with those? Why is it connected there on the synth and whatnot? This is a thing that trips a lot of people up when they start, and it's kind of just good to know ahead of time that it'll be a problem, but or not a problem, just something you have to figure out. The names of pins can be a big pain, figuring out what you actually connect your wire into, and what you reference in the code. That'll be probably the first place where you're like, I plugged the MIDI in and now it's not working. Go to the reference manual. The DAISY reference manual would be the one that you would find that info in, because it says these are the things that we expose on the DAISY, and how they all connect to the STM32 pins. And then if you were actually working on a driver or trying to edit the libDAISY drivers to make the audio hardware work differently or something, you would actually want to go into the STM32 reference manual. That's the sort of thing where if you're not getting audio out and you got it connected, keep that from there. That thing's like thousands of pages long. So it's intimidating, but it's your friend. But essentially, this is what's in the DAISY reference manual, and you start with the pinout value that we got, that 14 and 15 here, and then it actually maps in code to what the STM32 named those pins, and that's PB6, port B pin 6, port B pin 7, and the BC amplified here is the URC, which is, in our case, MIDI input. So there are two ways that that we can get this MIDI data from that multiplex pin to our program. There's the wrong way and the right way. Talk about the wrong way first. It's kind of like it's the more straightforward way. It kind of helps you. It's innate. It's something you can do in libDAISY. It's an option, but it's a blocking call. Basically, we read that pin over and over again. Again, that's where bare metal stuff kind of comes into play, because you're actually reading the hardware register over and over again. The problem is the CPU really shouldn't just be sitting there doing this over and over again, because you only have one core, and you need to be doing things like calculating audio coefficients and whatnot. But this is what it would look like in libDAISY to do the whole record. You got this help call here where you take in your newer terminal and a buffer that you want to write to, the amount of data that you want to wait until you have, and then timeout. Just didn't get anything. So there's a better way to do this. To have our program, instead of constantly asking for MIDI or expecting MIDI, we want to receive a callback when MIDI is written to that pin. And this also kind of brings us to a general concept in embedded programming. Like if you're a coffee grinder and you want your grinding routine to continue until some sensor in the real world senses that enough coffee has been ground, you would go and interrupt the program and say stop grinding. And then there's the classic example of the traffic signal. There's a book by Alicia White called Making Embedded Systems, which has a whole chapter on how this concept works using a traffic light. It's called interrupts in embedded terms. It's a fancy type of callback that is defined in the hardware, essentially. We won't talk about it too much, but because the mechanism is interesting, but the specifics of it aren't really necessary to know or to use them. In order to write your interrupts, you don't necessarily need to know how they work. Just know that you shouldn't do a lot of expensive stuff in them because they're actually interrupting your program flow. Oh, yeah, I'm sorry. Like wherever your program is, the state of your program will be saved, and then the interrupt will be invoked, and then your program will be resumed, because you're just dealing with a single core. So it's a very high priority type of callback in order to react to the real world. And you usually don't have to deal with things like the vector table of all the interrupts and reading registers. That's all handled by the STM libraries. So I felt like that just deserved a little background. Getting back to MIDI, we want to receive an interrupt whenever we receive MIDI, essentially. And the way we do that is using direct memory access. This is a peripheral you'll see a lot. It's really good if your platform has this. It's a peripheral that lives separately from your CPU. And its whole lot in life is just to service requests for data, and then whoever requested that data can go off and do whatever else they want to do. So the CPU just has to know where it wants to read data from, where to receive the data, and then how much data should be received. And then upon this amount of data being received, the DMA will throw an interrupt saying, you can buffer. And then the CPU can go do whatever, and it'll let us know when it's ready. And it looks, the help call ends up looking really similar to the polling interface, similar to TMA again. And in the DAISY case, we've got the UART peripheral in there, a peripheral of MIDI data in this case, and then the amount of data that we want to be notified about. So that is your drivers. Now I think looking at getting back to this flow diagram, I want to talk about how our program actually interfaces with that, and how it actually does something useful with the MIDI that it's received. So the program itself is really small. It's on GitHub for anyone who wants to build it, and it works with the DAISY. But there's really kind of 3 sections. It's like 250 lines of code. There's no initialization portion where we do all the things that we talked about earlier, where we multiplex the things we want to use. We initialize the audio hardware, like the MIDI hardware, or the UART hardware. And then from there, we just listen for MIDI, and the audio hardware calls us over and over again to receive audio. We have these things called voices. So every time you hit a key on the synthesizer, if a voice is available, that voice's oscillator will be turned on, and will start what's known as envelope. So if you've got an oscillator that's just kind of doing a signal at full blast all the time, an envelope gets multiplied against it, so that it kind of fades in, and then stays at a certain volume for a while, and then fades out. It's 50 for however long you set it to, with some filters and whatnot. If there are voices available, we'll start one. If you get a note off message, we'll kill the voice at that particular note. And then the rest of the lot in life for this program is to the audio callback will come back to our program and say, I need another buffer of data, and we'll give it however many samples of the current state of all of our voices together, in the form of floating point normalized audio data. Just for the sake of showing some code, the initialization part of this program looks kind of like that. Some just because the slide, but we pass in our audio callback saying, audio hardware, call this function, whatever you need, more audio. This MIDI start receive is a libDAISY call that will initialize the UART driver and multiplex the GPIOs. And then for the rest of the time, we just see if our buffer was written to by an interrupt in the meantime. And if it has, we will be populated with MIDI events and pass those in to a very simple handbook here. this handler only deals with two types of notes. So if someone says, I want you to do a trombone sound, we drop it on the floor. Just deal with note ons and note offs. Each note on will say what note it is, how loud it is, the velocity, and then the digital signal processing code actually lives in these two functions where we'll start voice and then write it over time. And then the third part is the audio callback, which is pretty small. The audio hardware comes in and says, I have this output buffer with that I want you to write in samples, floats to, and then we just run through our the state of our voices that many times. We take half the volume of that signal. Then what we have what's called a send. So we take a version of that signal and send it through a reverb here. This reverb is written by someone who is pretty well known in the audio community. Before he did, there's these audio plugins, these reverbs called Valhalla. Sean Costello. He wrote this algorithm for C sound in the late 90s, and it still sounds great, and it's open source. It's a cool reference if you want to check out the cool reverb. Then we just sum those together and put them back to the audio hardware. So we've got floats now. We've gone from MIDI to floats, and we need to turn those floats into digital audio data. And that's where we are at this point of the flow diagram. The digital audio data is yet another serial communication protocol called I2S. It is meant for sending digital audio. The audio data in that protocol is they're integers, not floats. And so each integer can store whatever amount of data resolution. We'll talk more about how the depth affects the audio, but these things are all configurable in the user code. Then there's a bit clock that works the same as the I2C bit clock. It says how long each bit of the audio data the clocks are. And then there's a special clock called the frame clock. And this has all sorts of names. There's CLR, CLK, word select, word. I don't want the next slide. I forgot, but it looks. That frame clock says whether the current audio sample is channel 1 or channel 2. And so that's useful because you're just getting a bunch of audio data. You don't necessarily know which speaker to put it on. So the audio data is here on the serial data line. These are the standards, like we said. And then the WS is the word select. So this says, this is one frame of left channel audio. This is one frame of right channel audio. You might see, a bunch of samples in a row that output the entire left channel and then the entire right channel, or you might interleave the samples. If you need to do something like surround sound, you have multiple I2S buses that put out multiple data lines, because it's only has two states. And then the clock line works the same as the I2S or the I2C, where it says this is how long one bit is. So the peripheral that can deliver this I2S digital audio data is the SAI, serial audio interface. That's a good term for graphing through documentation. But even if you're in Linux land and you want to know the driver for audio on your platform, if you search serial audio interface or SAI, it'll take you right to it. And the one on the STM32 has these two sub-blocks in it, A and B. Each one has an audio FIFO in it. And how the audio hardware determines whether it's going to send a DMA request to our program to get more audio data is when it has transferred enough digital audio samples out. It'll set this register freak, and that'll tell the CPU that it needs to deliver some another buffer of audio data, and that ends up calling our audio callback. We've delivered floats, so the bit depth comes in here. We scale those normalized floats to a particular integer value based on how much width we have to work with. And then in the Daisy case, these S2S screens come out on two locations. There is the internal one, which is kind of the whole reason to use the Daisy. You don't have to deal with the digital data so much because there's an internal connection and you can just get analog audio out. You can plug right into the speakers. But if you did have your own digital to analog converter, you could connect one using the SAI S2S interface on here, just like plugging MIDI and you can get wires with digital audio coming out of the thing. So, talking a little bit about how the Daisy does it, it has this SAI handler that you see in the code. You gotta multiplex the digital audio pins either to go to that onboard audio codec or to some other location and set some things like sample rate, bit depth, and what those are don't necessarily. I mean, they matter, but it's not crucial. And then the main thing that can really mess you up, I think, is the clock mode, because the synchronization for the audio data that you're getting or sending is either set by another device, or if you are the controlling device, you want to output a clock. And since there's only one wire for receiving or sending a clock, you need to set that mode right. Because if it's not right, then the software is going to be, either trying to read a clock when you're expecting to write something somewhere, and you'll just end up with garbage. So if you're looking in the Daisy, you want to start the Daisy seed, which owns an audio handle, which owns a series of SAI handles, and that's where all those guys are for weekend reading. So this is kind of what it looks like to start up the SAI config, setting sample rate, and the bit depth here is 24 bits, so you have 24 bits of integer to work with, and setting clock modes to either listen or generate. Either receiving audio, like if you are making guitar pedal and you want to have audio input and you're receiving a line level signal from there, or if you're sending audio, we are out of the send in response to MIDI. And then the pin multiplexing looks really similar to the UART cell. It's just GPIO, port E, pin 4, etc. And those also come from Daisy reference manual. So that's how we get the digital audio data. From there, we need to turn it into analog before we output it, because if you just output a digital audio signal, it would just be a really nasty square wave. That's where digital to analog conversion comes in. The two types of audio in our circuit are going to be analog audio, which is an AC signal, and that's just in contrast to DC, which is just one straight line of current. AC is kind of like a big old sine wave type of thing that is running at a particular frequency and it's continuous and whatnot. The digital signal is meant to try and represent the analog signal by storing little snapshots of that analog signal as integers. And those snapshots are voltage values as well. And this is where the bit depth comes into play. Because each of those integer samples corresponds to a voltage in the real world that's going to be output at a fixed interval. And so if you only have 8 bits to store a particular voltage, then that one number is going to quantize to the value that it really should be representing all the intermediate values. So essentially, more bits is more better. You get more accurate voltage output and more resolution audio. And DAC, DAC, digital digital analog converter knows how to translate those integers to voltages. That's its special role in life, and then those voltages are what drive the speaker. And even at that point, the audio is not sound. If that makes sense, it comes through as an analog AC signal. It's electricity going through, and then it hits a magnet, and then wiggles that magnet, and that magnet wiggles air particles, and then those air particles hit your ears and wiggle your cochlear membrane, and then that's but all that stuff doesn't have to be done by the day. That's evolution at work. You'll also run into the term audio codec fairly often, which is a confusing term when you're starting out, because in this context it's not compression decompression like MP3. It's meant for encoding or decoding integers in an analog signal. So you'll see this if you're shopping for components or something. I want to buy an audio codec, which is the audio codec on this board or whatnot. You'll see that more often than digital analog converter, especially for audio specific type of hardware. Oftentimes they'll have both directions. So if you've got an analog signal and you want to make it into digital data, you can input it there. It also has often an amplifier on board. And the Daisy has two, like we said, there's the
Battery under quarter full.
there's the one on board, the AKM 4556 that sounds pretty good. There's not much reason to use a digital one, but if you have these upward bands, you can also get this digital data from those. Yeah. By the way, this is a practice talk, so I'm making mental notes of all of the bullet points that I don't need. So that's why I'm skipping a bit. There's a picture. So these are the analog notes, analog audio coming out. These are coming from this audio AKM codec here, sending left and right audio. And then this is digital audio that you connect wires to and actually plug into some other breakout board. You can use either of these. You'd have to configure into the code where you're actually sending your audio to. By default, I don't think these are enabled, at least the last time I checked. So I think the Daisy team is working on that. This is the internal version. This looks a lot like the picture that we showed at the beginning, where we're actually getting audio out from these two pins up here, analog audio. So you can plug this right into your receiving device. This is a speaker plugged directly into these guys being amplified. That begs the question, how do those amplifier circuits work? I think it's worth talking about a little bit. They're based on a operational amplifier or op amp. A really cheap thing if you're looking to put together a high value audio project. It's good. You just got to order these. The LM386. Circuit's pretty easy to build. There's I took it from this Tales from the Chip article on Instructables. It's easy to build and tear down and whatnot. That's what it looks like on a breadboard. So I've got two of those next to each other to get a stereo signal. And if you want to go the digital route, you can get one of these guys from SmartFun. It's got the digital data coming in to this guy, and then the speaker coming out of here. There's an amplifier, and this is taking the digital data and showing you it analog.
So, do you have both wired up on your board?
This one,
Is that two different?
they're two different circuits, yeah. Yeah, I don't know if you can tell with my wire management, but I haven't really figured it out. I've seen pictures of people who are really good at having their breadboard space optimized, where they can have just all sorts of things. But I've got wires going everywhere. It helps if you cut your own wires. Let's see. I do have an audio sample. I don't know if it will work, but I'm gonna try it just so we can at least hear this thing. We'll see. It's probably trying to come out to HDMI, but that's okay. I can try the laptop because it's smaller. So yeah, this is just 200 lines of code. And right. It's hard to hear like the reverb, but thank you. But the built-in algos in that Daisy SP library do sound really nice. Anyhow, that's kind of the whole synthesizer. I was just gonna end with kind of next step type stuff. Just gotta. There we go. Okay. So I guess quick review of all the signal flow, this stuff. We talked about the MIDI coming up here, the digital UART data, the output by the synthesizer here, coming through a 5-pin MIDI DIN connector, coming into this breadboard little connector here, going into our MIDI input circuit, being converted to light, and then back from light to an electrical signal of ones and zeros that are being sent from this kind of agreement wire into pin 14 or 15, I can't remember, but going into our program through the UART driver, our program cranks on that MIDI data and puts these voices into place, and then the audio interface here on the microcontroller just continuously, when it needs audio, calls our program to get more, and then it sends those over to this audio codec down here. So I guess in this case it wasn't wired up to do that. The audio is coming out here on these 3 wires, and going into the SparkFun device, and then coming out as analog audio and getting playback. So, if that inspired any tinkering, there are some good Daisy tutorials, kind of specific to their hardware if you decide to get their things. You can do all this stuff with a TC or a Arduino, or you can make your own board. I'm not sponsored by Daisy, I just really like them. But, and they don't, it's not like a whole book, they just kind of have a couple of tutorials on there to show you how to hook up buttons, because this synthesizer just makes that one sound. It doesn't have any knobs or anything. You would use GPIOs with connect up to the ADC inputs to be able to like change the length of the reverb, it's like the tag time. Things faded in really slowly, but you could make the tag time really slow so that when like notes came in like plucks, that sort of thing. I'll mention this again, make electronics. Setting up your lab is going to be crucial, kind of getting some breadboards, getting up to put all of your stuff. I spent so long with like the bags that they send you from DigiKey, just all over my floor. And got a lot more sane when I got a little plastic container for it. And it teaches you, things about soldering, what that sort of stuff. There's this Alicia White book that I mentioned, Making Embedded Systems. That's kind of more in depth, and it is kind of more industry focused. It goes through here's how the prototyping phase happened. It goes all the way to power management and things that I didn't talk about. I talked about more about the hobby side of things. And then we didn't mention embedded Linux as well, and so I wanted to do a shout out to this book because that might be a logical next step. It's not really tiered in that sort of way, but if you, especially if you know Linux already and you wanted to do this type of stuff, it'll show you how to build Linux itself and build your program into Linux and how you do it as you roll your own Linux and then do all this crazy stuff. It's a good resource for that. Practically speaking, you want to get your tools, you want to learn about breadboards. I just realized we didn't actually really explain what breadboard is. These actually used to be, back in, I don't know, whenever they were invented, actual breadboards. pieces of wood with nails sticking out of them, and you'd make these temporary electric connections between things when you didn't want to solder stuff. It allows you to set up the circuit really quickly. If something's not connected right, you don't have to melt it apart, you just have to unplug the wire. And basically you got power coming down here, so if you take a wire coming out of any of these, you can get a ground connection from one of these, or a power connection from here. And then each of these rows, you can connect things in series of parallel based on configuration. It makes more sense when you're actually looking to set up a circuit. But I also explain series of parallel. But the power section, I actually want to shout out to, because if you don't do this, this section of the breadboard, it's up here. It's a little switch and an LED, a light, and a resistor, so you don't blow up the light. That's actually one of the first steps in that Mega Electronics book, is blowing up an LED, because why would you put a resistor in front of it? But if you don't have this, you'll have to plug in 9-volt batteries to all your things all the time, and you'll wonder if they're actually working. And every time something goes wrong, you'll have to debug your power. And so if you just have a switch to turn things on and off, and have a DC wall work into a wall, you don't have to get up all the time and unplug it. It's can't recommend it enough. And then you just pick, or you can use Arduino Teensy, what you're going to build. If you can do an audio thing, you just might use, guitar pedal, you have guitar audio going in and audio coming out. Arpeggiator, you have some buttons on here that you press, and they produce MIDI on the synthesizer case that we're talking about, where you're inputting MIDI and getting audio out. The world is your oyster. That's the talk. The code's on GitHub. Thanks for listening, and I can try to field some questions if there are any. Yeah.
Yeah, so I'm curious, the audio call out coming in from hardware. Do you run into any cases where you can service that quickly enough and you have drops or distortions?
That is kind of the, like when you're writing an audio algorithm, like the main thing to worry about. But this program is so simple that I didn't write into that. But yeah, that's when you know to optimize, when you get running against hardware and that sort of stuff. You won't run into things like dropouts, obstacles, that sort of stuff. Yeah. And then actually, the audio callback is an interrupt, and like all other interrupts, it's something that you want it to be as lightweight as possible because it's interrupting the program as well. Yeah.
Not being an embedded program, hopefully it's not too weird question. What kind of C++ are available to you? C++ 17, 20? Or what kind of C++ can I use to do this?
It depends on what the particular compiler for the processor supports. I think I was using C++ 17 when I wrote this just a couple years ago. I don't you can use Rust on this board too. So I think you can do not like you know what I mean. Like you can do probably a lot of stuff. It's just hard to have so
Yeah. If you're targeting ARM chips, you can use GCC, which means you have up to 20 all with stuff.
yeah.
Just more a general comment. Alicia White also has a really nice podcast called Embedded Film. Yeah, if you like, I haven't read the book thoroughly, but if you like the book, I really do recommend it.
So I've actually been a guest on that podcast. I'm like, why do we know that now?
Was that a long time ago?
Yes.
I vaguely recall this. It was like 2017 or something.
It was a long time ago. Matt referred to me, I think. But it was a long time ago.
Continue on C++ 17 or 20. So when I see stuff like events happening on the system, I think of nowadays coroutines. For example, can this run coroutines and will it be useful to dropouts or in terms of performance? Can it handle, I mean, coroutines supposed to have, we can have millions or billions of them. Can such a system handle coroutines?
Well, I've never tried it myself, but I mean, I imagine it should. Yeah. Yeah, I don't know, but worth a try.
Yeah, embedded folks tend to be really cautious about any sort of dynamic memory. I don't know if coroutines use.
They do require.
They do require,
Yeah, like a lot of embedded systems are really, really hesitant about dynamic memory because it leads to memory fragmentation, especially when it's supposed to run for a long time. So I think people would tend to shy away from it. I've never tried it myself.
But if you set it up and it was just one that ran forever, it's only one application.
Yeah, exactly.
That's possible.
Event systems seems to be coroutines and so
Yeah.
Yeah, definitely.
Well, I didn't talk about it too much. Actually, this talk is for mainly for a audio conference later, but if I had done it mainly for C++, we know, but I'm going to talk about all the C++ implications because there's kind of this war of conceptions and maybe it's best if I don't go into that. But yeah, the resource constrained environment of the embedded program does make it kind of a subset that's required. You know, some of that's valid, some of it's a carbon called. I don't know.
Yeah, like as a point of reference, that chip is like 400 megahertz. So like, if you're used to working in a place that has 3 gigahertz processor, it's not the same environment as far as any additional overhead can make a big difference.
But it's way faster than a 1 megahertz.
Oh, totally. Like that chip is like, light speed compared to a lot of other things out there. Which is great for applications like this.
Yeah.
When is ADC? When are you doing this?
Is November. I don't remember the exact date. Early November.
Are you going to London for it?
No. No. I could. Yeah. I don't know. It'd be a good excuse to go. But they're doing a hybrid remote, so you can do it from anywhere. Yeah.
I have very low isolated for this need. Do you have to look for something that is it constrained by the capacity product?
I think so. I think that MIDI comes in so slowly that it probably works really well for that. But yeah, we should activate the data sheet, so. Yeah, there's no problem. There's the main ones that I've seen out there are the S6N 138 and 137. And the 138 I think is actually, it might be in the spec. I'm not sure about that, but the 137 was part of myself, so that's what I kind of thing. I just really pushing smartphone today. Yeah.
I was curious when you were working on this, you found like really, maybe in their code, but is it like a really good example of using C++ embedded system? Like always a better example of like how
It is.
you can design code.
Yeah, I mean, it's a very, for what it is, it's a pretty simple code base, which I think makes it really good for learning embedded concepts, because you don't get kind of stuck on like a scene or a paradigm that you're not familiar with or whatnot. And the layers of abstraction above the actual dealing with the hardware are so small that it kind of shows you how to write your own abstraction layer over a really clunky abstraction layer. So it's good for that sort of thing. And the DSP library can be good for learning DSP and audio programming type of stuff, but the problem with math code is that usually it's been through the optimization ring to the point where it's hard to reverse engineer into like why they did certain things. But the hardware library is really good for learning about using analysis and stuff.
If I read the spec right just now, since someone just asked, it looks like the 136 opto isolator can do 10 megabyte, which should be plenty fast for the applications you're talking about.
Yeah. That'd be a fast light. Yeah. Is that all? Seems like it. Well, thank you all for coming again. Really appreciate it. And thanks for the meetup. Yeah. See some of you.